Thank you very much for being here and welcome to my talk. I am grateful for the organizers of the conference for the opportunity to be here and for the opportunity to deliver and the talk and present our science about measuring the strength of the Lewis society and what the experimentalists actually measure. So, Lewis acids. Lewis acids are characterized by the presence of the empty orbital, and this type of compounds are extremely important in the chemistry, but also in catalysis, where are also coming from, because Lewis acids are the catalysts which catalyze a huge class of chemical reaction, starting all the way from the very classical ones, such as Friedel-Crafts tetraphilic substitution, acylation or alkylation, or any condensation reaction involving carbonyl compounds, such as aldol additions, etc., etc. But not just also classical reactions, but let's say the modern chemistry, I don't know, enantioselective catalysis, which is extremely important for the pharmaceutical industry. Or, of course, if we are talking about industry, we cannot not mention we have to mention the heterogeneous catalysis, because most of the heterogeneous catalysts employed in the chemical industry are Lewis acids, alumina, zeolites, metal oxides, zinc oxides, zirconia oxides, and many, many more. But when we are talking about Lewis acids, we're not just about themselves as the catalyst. We're also talking about their strength. And why do we are talking about their strength? Let's, for instance, again, consider this Mukayama-aldol addition reaction. If we use a Lewis acid, which is too weak, that means there will be no reaction, nothing will happen. If we will use the Lewis acid, which is too strong, we will get things like irreversible substrate binding or more nasty stuff could happen. So as such, we want to use a Lewis acid, which is of the optimal strength, the one that have a good amount of strength to catalyze the reaction and good amount of strength to not irreversibly bind to the substrate. How do we measure this strength of the Lewis acid? In DFT world, in computational chemistry world, it's actually quite simple. You take your Lewis acid and just attach the fluoride ion to it and measure the strength of the interaction of this acid with the fluoride ion. Obviously, if you try to expose the real compounds to the fluoride ions, you can expect the irreversible destruction happening. As such, the experimentalists came up with a different method of using measuring the Lewis acidity, which is Gutmann-Beckett method, introduced by obviously Gutmann and Beckett. And its idea is extremely simple. You take the prop molecule, which is 3-ethyl phosphine oxide, and you add the Lewis acid, which forms an adduct, and you report the difference of the chemical shift. The difference is of the chemical shift between the adduct and the bare TPO molecule. So as such, you can, for instance, measure the shift of the chemical shift, delta delta, of the different compounds and make like a tier list of the Lewis acid characterized by the delta delta delta. The smaller the delta delta, the weaker the acid, and vice versa. The problem comes when if we will compare this descriptor of the Lewis acidity with mentioned fluoride affinity. As you can see here, the Lewis acid, which is the strongest one in terms of Gutmann-Beckett method, appears as the weakest one in terms of the fluoride ion affinity. And you can see there's a huge discrepancy between these two axes. And if we will generalize on the wider spectrum of the Lewis acids, you can see that there is no correlation at all. As such, it is important also to ask so this is the Gutmann-Beckett method is the most widely used experimental technique. As such, one wants to ask, what does this delta-delta value actually measure? What does it report? And that was the goal of our work. So to establish the correlation between some metrics and the observable delta-delta, we want to explore a wide range of Lewis acids. So we, as the data set, our initial data set, the molecule data set, we try to make it as diverse as possible. And by diverse, I mean we want to include the Lewis acid of different, which had this different coordination environment. So 3-coordinated one, 4-coordinated one, 5-coordinated one of different central metal chemistry. So it could be boron, aluminum, all the way from the top periodic table to the bottom, and of course transition metals and different charge composition, either neutral ones or cationic ones. Of course, I mentioned the importance of heterogeneous catalysis, so we also included the systems which mimic the heterogeneous industrially used systems. As for the methods, so we for the calculation of the chemical shift, we use the fully relativistic treatment for component Dirac-Hamiltonian, simply because we have to use relativistic treatment. Otherwise, the chemical shift for the compounds involved in the bottom part of the periodic table will be unreliable. And to do the molecular orbital analysis, we used NBO as it is one of the most, let's say, chemically interpretable frameworks of the decomposition schemes. So let's again go back with to the interaction of 3-ethylphosphine oxide with the Lewis acid. So we have let's say, there is 3-coordinate Lewis acid. It interacts with TPO, and it forms this basically tetrahedral complex. As such, this process can be decomposed into two ones. One is the first, the deformation of Lewis acid, and the second one is the interaction of this deformed Lewis acid with the TPO molecule. And obviously, one can say that there is no correlation simply because this deformation energy for the different Lewis acids is different. And it's since chemical shift of phosphorus is the intrinsic property of the phosphine oxide, obviously there will be no correlation, and one can be right, of course, but this answers question. This answers the question why it doesn't work, but we don't want to answer this question. We want to answer the question, what does the chemical shift report? So for this, we have to look deeper into the electronic structure of the 3-ethylphosphine oxide. And there was a huge debate in the 90s about how we should represent the, let's say, electronic structure on a paper of these phosphine oxides. And the most consensus were reached into this resonance structure, in which we have one single dative PO bond and 3 lone pairs on the oxygen. And if we zoom deeper into these oxygens, we will find quite interesting features. So let's zoom into these 3 lone pairs. One lone pair is just a regular, let's say, S-type lone pair with a high S character. And these 2 lone pairs, N2 and N3, has an interesting property in which they donate some of their electron density into unoccupied sigma star PC orbitals. So one can imagine this as components of the PO pi bond in a Lewis scheme. So these 2 are delocalized, and that stabilizes the structure of the phosphine oxide. Otherwise, the repulsion between these 3 will be too high. If we bond these, what happens with these 3 lone pairs if we will try to bond them to the Lewis acid? So this one is simple. So because it's coaxial with the PO bond, it just basically transforms into the sigma bond between the Lewis acid and the oxygen. This is quite trivial. But for these ones, we can see that once we bind, the degree of the delocalization, degree of the donation of the electron density from the oxygen lone pairs to the PC sigma PC star bond is decreasing. So we can imagine that, again, maybe it sounds trivially, but we weaken the PO bond, its pi component. We want to learn how this weakening happens quantitatively, and for this we use the one nice feature of NBO analysis, which is called deletion energy. And deletion energy is quite simple. As such, you just calculate the energy with a certain Fock matrix element equal to 0. So basically, you turn off this delocalization and make these electrons delocalize heavily on the oxygen, and thus you just remove this pi bond. And if we put this deletion energy against the chemical shifts, you can see here now it's more matching. So the strongest Lewis acid in terms of Gutmann-Beckett method is also has the lowest deletion energy. That means its PO pi bond is the weakest one. This is nice, but if you also try to put this into linear plot, it's much better. People from the machine learning from the machine learning field would say it's quite nice correlation, but it's still not, R square is still not equal 0.9, which we usually deem as nice, very nice linear correlation. So we try to dig deeper into maybe we missed something. And for this, we need to go back to the basics of the NMR and remember that NMR is not a single number, simply because NMR reports let's say, the shielding of the nuclei, and of course the shielding is not always spherical. It can be anisotropical, like in this case. And in the solution, only one number reported because it's all averaged. But in the solid state, we actually do not see one signal, but we see three signals corresponding to three principal components of the chemical shielding tensor. And if we want to try to see which one is the most meaningful one, we can plot them against the isotropic chemical shift. And we can see here the strongest, the one which changes the most with the change of the isotropic chemical shift, and also the one which most correlate is the one, the 331, which is located along the PO axis. So, and the nice thing about NMR, unlike the abstract stuff from NBO, is that NMR is actually observable. That means that we can ask our experimental colleagues to run a solid state NMR and confirm that basically once you expose your TPO to the Lewis acid, the component of the chemical shielding tensor that changes the most is the 331. So the theoretical observations are confirmed, and if we put 3,3 component, the most responsive one, against the deletion energy, which is the measure of the weakening of the PO pi bond, we can see a nice number here again in the R square. So from this, we made a conclusion that delta 3,3 in the Gutmann-Beckett method is not reporting the PO bond weakening, but it is reporting PO bond weakening, but it's not reporting the binding energy. Doesn't matter? Actually, yes. If we go back to this scheme, of course, sometimes we want to use the thermodynamic descriptor such as fluoride affinity to see if how strongly the Lewis acid will bind to your substrate. But sometimes we also want to use this descriptor of the induced bond weakening to see how strongly your Lewis acid activates the bond of the substrate. And this, what Gutmann-Beckett method is actually could be quite useful. The problem is with this delta 3,3 is how to observe it. Of course, one can always do the solid state NMR with the magic angle spinning, but this experiment is quite expensive to make because you need a special probe and special NMR probe and special ampules to do this. So, of course, there must be a way to make this much cheaper. And we can also deduce this from computational chemistry side by knowing that from the T1 relaxation experiments in NMR, one can get what is known as a chemical shift span, which is basically the difference between the most deshielded and the most shielded component of the chemical shielding tensor. And knowing the formula for the isotropic chemical shift, one can derive the expression for the delta 3,3 in terms of isotropic chemical shift span and the 2,2 component. But after looking through our data, we can see that delta 3,2 contribution is always more or less the same in delta, so we can just omit it and express the delta 3,3 value in terms of only isotropic chemical shift and the span. And this approximate delta 3 value Again, it's very nice, not 0.9, but still, we can, from looking at theoretical data, we can see that solution NMR can approximate the solid state result very well. In the end, what I wanted to say, my take-home messages for you are, so Gutmann-Beckett reports not how strongly the Lewis acid binds to the your phosphine oxide, but how strongly Lewis acid activates the bond in your substrate. And of course, and this can be reported, that can be learned either from the solid state NMR, but there are the approximate techniques to learn this from the perspective of the solution NMR. I will, of course, one can never do such work alone. So I want to, of course, to thank our my supervisor Evgeny and his wisdom, and also I want to thank our experimental collaborator Matt from the University of California, Riverside, for his wisdom and for his experimental efforts. And this work, of course, is an open access. It's published in JAX, so feel free to read it and learn. Thank you very much.